14.2, we're going to take a look at something called Euler Circuits. That is not Euler. Don't say Euler, that's not his name. His name was Euler. He's a mathematician. Euler Circuits. And here's our leading idea. Euler circuits involve finding a path that visits every edge of a graph exactly once and returns to the starting point. A journey of completeness. In a similar way, faith in God can be seen as a spiritual journey seeking wholeness, where every experience and challenge is a part of a purposeful path that ultimately brings us back to Him. Just as Euler circuits remind us of the importance of connection and balance, God encourages us to trust Him in His plan. So they've got some details, even within the leading idea here, we do, of what this does. It visits every edge exactly once, and it returns to the starting point. That's what an Euler circuit's going to do for us. So we're actually take a step back then and describe what an Euler path is. An Euler path is actually a path that uses every edge exactly once. And we talked about paths before. Paths just means you don't repeat edges. But in this case, you actually cover all the edges as well. Euler circuits cover all the edges, so you walk along all of the different edges, but you also return to the starting spot, as in what a circuit means, like we talked about before. So if you want, for the purposes of what we're looking at, to think about this word Euler, and that's not what this word means because this is a guy's name, but what we're connecting this to is the idea that edges are all crossed. You go across all of them. Okay, no edge gets left out. No edge gets left out. You might have heard of Euler before. Euler typically shows up in a geometry class. He has to do where it shows up there is a three-dimensional geometry. And he's known for establishing, in that sense anyway, the relationship between the edges, the vertices, and the faces of a three-dimensional figure. So imagine a cube, right? You've got the cube and it's got 6 sides like a dice. And then it has the edges, and it has 12 edges. 4 on the bottom, 4 around, and 4 at the top. And then it has 2, 4, 6 vertices, right? Corners. And there's a relationship that exists for all three-dimensional shapes like that talks about the edges, the vertices, and the faces, and it equals 2. You add 2 of them together and subtract 1, you get 2. Euler is also known inside of graph theory, though, for paths and circuits in this regard. So let me draw in the image, the graph that we're working with here. So for those of you with the printout, did I miss anything? Did I get them all? Look good? Okay. So our question is to consider this graph and decide if we have an Euler circuit in what it's given. And if it fails, we're going to identify why it fails. My math lab likes to ask you those kinds of questions sometimes, right? It asks you, does this graph, or it'll do it for graphs now, but does this situation allow you to use this fact? And then it'll give you multiple choice answers. And one of them is going to be yes, and it works. Right? You guys remember when you did the tautology? Is this a tautology? And you had to say yes. And if it failed to be a tautology, you had to say why. Do y'all remember those questions? It's going to do the same thing on these questions. It's going to ask you yes or no, and if it fails, you're going to have to say why. So the first one, we'll follow along with colors, and we'll delete them, or we'll change colors as we go. So it says we're going to go from A to B, and B to E to D, and D back to A. Is that an Euler circuit? Okay. So be careful. There's two conditions. One condition is Euler, and one condition is circuit. Circuit means it starts and ends at the same point. So for those of you who said yes, that's probably what you were looking at. It is a circuit. But it's not an Euler circuit, because an Euler circuit has to cross every edge in the graph. And we missed a whole bunch of edges, didn't we? We definitely did. So this one is not an Euler circuit, so it's no. It is a circuit. So write that down for yourself, because if you look back at this later and the answer is no, you're going to be like, wait a minute, I thought it was. Well, it is a circuit, but it fails to use every edge. Does that make sense? Okay, let's look at the next one. It's A to B, B to C, C to D, D to E, and E to G. Is it an Euler circuit? No. This one fails on many, many counts. Somebody tell me something that was messed up in what we did.
It went B to C.
It went B to C. What's wrong with that, Jonathan?
There's not a line connecting B and C.
There's not an edge there, right? I essentially walked in the grass. You know when they put the signs and they said, do not walk in the grass? We did it. We got off of the sidewalk. That's not cool, all right? So no, so B to C, and it happened on C to D as well. B to C and C to D aren't edges at all. So this isn't even a walk, because a walk would mean that we actually went through on the edges. We stayed on the sidewalk, and we didn't do that. So this one it's not even a walk. So B to C and C to D are not edges. What else does it fail to do?
Return.
Yep, you bet. It fails to return to A. So it's not even a circuit. It fails one more thing too. It doesn't go through all the edges, right? So it doesn't use all edges. So you want to be sure that when you're looking at the multiple choice answers that you recognize all the ways it fails, because undoubtedly there's going to be answer choices that are going to identify one of these things and not all three, right? And this fails on 3 counts, and we want to make sure we recognize all 3 of them. Okay, we got one more. I got my same picture over here. Let me copy it. Excellent. All right, let's go through the letters. Let's see, we're starting at, use green. A to B. Actually, let me try and take this one off because we don't need those edges showing up there like they're there. Okay. A to B, B to E, E to F, F to G, G to E, E to D, D to A to E, E to C, and C to A. Yes. And the reason is because it met all those criteria, right? It returned to A, and it crossed or went through or used all edges. And it didn't walk through the grass. Absolutely. It stayed on the edges. You bet. Huh? Yeah, it would be a path, and it has to be a path in order for it to actually be a circuit. So that's sort of like a lesser condition. The fact that it returned gave us that circuit status as well, but you're right, it's also an Euler path. Correct.
Is path the one, was it walk or path the one that you couldn't?
Walks means you can't get off the sidewalk, okay? Path actually means that you are getting there without crossing edges twice. All right, Euler's theorem. Euler's theorem says the following. Suppose we have, my watch is dead. Suppose we have a connected graph. 1, if the graph has an Euler circuit, then each vertex of the graph has an even degree. Okay, so we actually found that one, the last one. It had an Euler circuit. That was number 3, you know, the C, the third option. It was an Euler circuit. So if we were to go back and we were to count it, we would actually find that every vertex has even degree. But not only that, step 2 says that if you have even degree, you are going to have an Euler circuit. Okay, so this is a bidirectional statement. That doesn't always happen with things. If and then statements. We've encountered lots of them. We did them back in chapter 3, right? If my daughter leaves her shoes on the floor, then they get taken. Correct? Y'all remember that? I even showed you a picture of it happening, didn't I? Right? But just because her shoes got taken doesn't necessarily mean she left them on the floor. Maybe she left them outside in the driveway. Right? Doesn't work both directions. But this does. Even degree of all the vertices means I have an Euler circuit. Euler circuit means I have even degree on all my vertices. And part of the reason that that sort of should make sense or resonate with us is that in order to be a circuit, we have to be able to go into the point and we have to be able to exit out of it. Right? So you think about our room, I've got to be able to come in one door and out the other. I can't go out the same door if that's representing an edge, because then I would be crossing over that edge twice. And that's what I'm not allowed to do. Okay? So it kind of makes sense that these have to have two, they come in pairs, they're evens. If I go into the point, I have to be able to go out of the point. Okay, am I good to switch the slide? Oh, one more. Sorry about that, Jonathan. Okay, so our graph this time is a square with a point in the middle. Your edges are straighter than mine, but that's okay. Remember, the edges don't have to be straight anyway, so it's an irrelevant feature. Okay, here's our graph. Question asks us to use Euler's theorem to decide if it has an Euler circuit. But it doesn't actually ask us to find the Euler circuit if it exists. We're just deciding if it has one. So what did the theorem on the previous slide tell us was the determining factor if something had an Euler circuit? Even degrees on all vertices, right? Okay, so let's count. What's the degree of A? 3. That's enough to fail, right? But just for funsies, let's actually find the rest of them. How about D? 3. C? B? E? Oh, one of them had even degree. That's not enough, right? We need all of them too. So the answer is no, and it's because at least one, and we have a bunch, but at least one has odd degree. Easy to check, especially if I'm not asked to find it when I'm done, right? Even if they'd all had even degree, I would still be done at this point, and I would say yes. Okay, we're going to take that idea and go a little step further on this one. We've got a bow tie picture. First directions, use Euler's theorem to determine whether the graph has an Euler circuit. Let's just do that, and then we'll follow with the rest of the directions. So how did we do that? Count the vertices degrees, right? So how about G? I has 4. J, 2. K, and H. Okay, does this have an Euler circuit? Yes. So this one has an Euler circuit. All right, what's it say next? Then determine whether the graph has a circuit that visits each vertex exactly once, except returning to its starting vertex. Okay, so that's sort of like this extra condition. We know it's going to have an Euler circuit, but does it have one that does this extra feature? And if so, we're going to write that circuit. So we want to start, well, it really doesn't even matter where we start. We're going to start somewhere, okay? And we're going to try to cross all the paths, which we know we can, without crossing any vertex twice. Yep, that's not going to happen. If you want to try, you can start with G, and you can go down to H and up to I. You can't go back to G because then you'd be stuck. You'd be done. So you can go over to J and then K, and then you go back to I, and you've crossed I twice now. And you're back to G. And that will happen every single time you try it because there's 4 vertices here in the middle at I, or 4 edges, excuse me, here in the middle at the I vertex, right? I'm going to have to go in and out of this point twice. Otherwise, I won't cross all 4 of those edges. So there is not one. Can these read that green okay? Or should I change it? Is that right? Okay, not one that crosses or passes through or whatever kind of phrasing you want each vertex once. There's not one. Okay, let me get you to write down a cut edge definition and then we'll push pause for today. A cut edge. This is an edge in a graph whose removal, if you cut it, right, if you removed it, disconnects the graph. In shorthand, that's what it says. If you cut that edge, right, you cut that string, you tear up that sidewalk, you can no longer get from point A to point B. Somewhere in the graph. Right. Our road systems make sure that this doesn't happen in the US, right? Y'all know it. If you've driven on I-40 for the past like 10 years, the thing is all messed up at somewhere along there, right? But they're careful that it can still be navigated, even if it's one lane, right? It hasn't completely disconnected that highway. That's what we do. By the way, that's not common to all countries. Ethiopia doesn't do it that way. They just shut down the road and you gotta figure it out. It's really tricky, okay? So that would be considered a cut edge if they actually shut down I-40, okay? So an example of one, so I can show you what that looks like. Let's say we have this graph. Can you identify an edge that if I were to cut it, if I were to take it out, it would create 2 unconnected pieces? Gabriel. B to E. B to E would do it. This one right here would work, right? If I break that apart, I've got the piece along the top, and I've got the pieces at the bottom. What else? Mark. D to E. That'd do it. It'd break apart. What's next? D to G even. D to G, it does it too. It breaks apart just one vertex, or it makes an island out there in the middle, but that still is part of it. There's a ton of them in this graph that are cut edges. Let me draw you a graph that has none, though. Every edge that you cut in this graph doesn't disconnect anything. True? Not if you disconnect, if you only cut one, it doesn't disconnect things, right? Okay, we're gonna pause there for today. The video for the last part that we have, and here's why. It has become abundantly clear that when you guys have homework due on the same day that you have a test due, it doesn't go as well. Truth? Yes. So I really want us to try to stay on track with getting the homework done completely before the tests actually happen. In order to do that, we need this to be short and be posted online, okay? So homework, whatever number we're on, are we on 9? Homework and quiz 9 will still be due on Tuesday. All right, I'll post this video. You'll have it. I'll send you an email to let you know.